Hey, grade 11s, we've been spending some time working on alkanes, and we knew that alkanes had all single bonds, and when we named them ending in -ane. But I've also told you that organic compounds can have double or even triple bonds between the carbon atoms. When we have a double bond, we are making something called an alkene, and a triple bond is called an alkyne. So we have a couple of new name endings for us to pay attention to. Today I want to talk to you about how do we name alkenes and alkynes. Remember that every syllable in chemistry has a meaning. So when we are trying to define these, alk refers to our alphatics, or our straight chains. And remember that the word straight is always used in brackets because in reality they're not perfectly straight. We know that they can bend corners and twist up on themselves, although we quite often draw them stretched out to make it easier for us to name them. Ane refers to, or E or ine will refer to the type of bonding. Ane means that we're going to have all single bonds between the carbon atoms. Bene means that we're going to have at least one double bond. And if it ends in ine, that means there's at least one triple bond. So these are all alphatics. And we're going to remember that the ane, ene, and ine is going to refer to the nature of the bonds. Now, is it possible to have double and triple bonds in the same molecule? Yes, it is. Are we going to do that in high school chemistry? No, we are not. We are sticking to the basics of the naming. So when I have to name something that has a double or a triple bond, I start like I did with the alkanes. I start by finding my parent chain, and it's the longest continuous chain of carbons I have that contains that double, or in the case of an alkyne, triple bond. So I've got to highlight right through it. And then I'm going to change my parent chain name to ene if I'm dealing with an alkene, or ine if it's an alkyne that we're building. I also have to say where that double or triple bond is because obviously it can move around. From now on out, because we have something called a functional group, something that changes the name of the alkane, that always gets precedence in our naming. So the functional group in our case will be the double or triple bond, and it will always have to be given the lowest possible numbering. When we had alkanes, the only thing we had available to get the lowest numbering was the branches. Well, now some of our branches might have very high numbers because the functional group gets the lowest numbering. If we have more than one double bond, if I have two of them, I'd call that a diene. If I had three of them, I'd have a triene, etc. And if it was an alkyne, dienes and triines. Let's take a look at some examples. In all these cases, one of the best things we can do is pick up our highlighter. Our highlighter is always our best friend when it comes to organic chemistry. Find the longest chain that contains your functional group. In this case, we highlight 2 carbons. The word that means 2 is F. The fact that there is a double bond, we end the name in ene. In this case, we have propene. Prop because 3 carbons, and again, ene because there's a double bond. In both of these cases, I have not written a number. In both of these cases, we would have to have these labeled as 1 ethene or 1 propene. Because if I chose to draw it the other way and number from the opposite side, it would still get the number 1. In this case, it doesn't matter if I number left or right. We have the double bond between carbons 1 and 2. With propene, the way I've drawn it now, I would number in this direction. But numbering it in the other direction, by moving the double bond to the other side, just means I would have to number from the opposite side. Remember, your functional group always gets your lowest numbering. So with butene, We could have 1 butene or 2 butene. You notice now that there are 2 separate choices that we can have for naming butene. It is not possible to have 3 butene because at the point that I tried to move my double bond over one more space, I would be numbering from the opposite side. I'd be numbering it from the wrong side. With pentene, I can have 1 pentene or 2 pentene. Again, trying to move the double bond over just one more spot. For example, putting it here is still 2 pentene because now I choose to number in this direction as opposed to this direction. Both of these would be 2 pentene. In this case, we have 2 double bonds. One of them is between carbons 1 and 2. So we're going to pick the number 1. The other one's between carbons 3 and 4. So we pick the number 3. Always pick the lowest possible numbering. This is 1,3-butadiene. The word di or tri always goes immediately in front of the part of the word that's doubled. Since what we have 2 of is 2 double bonds, it's a diene. You would not say dibutene because I don't have 2 butene chains. What I have is 2 double bonds. Once we have named our organic structures with a parent name, we can then name any branches that might be sticking out. In this molecule, this is my parent chain. We can see that it has 1, 2, 3, 4, 5 carbons, and so we use the prefix pent. There are double bonds, so because it has double bonds, it ends in ene, and because there are 2 of them, we call this a diene. This is pentadiene. But on this pentadiene, we will also see that we have a branch. This is my methyl branch. Now, numbering my chain, I can see that the methyl branch is on carbon 3, and that my double bonds are between 1 and 4. This is 3-methyl, 1,4-pentadiene. Remember to include dashes to separate numbers from letters and commas to separate numbers from each other. So working this through, we're always working our way from the back up towards the front. Let's try a couple more together. Suppose we have a structure that looks like this. I'll start by putting 5 carbons. I'm going to put a single carbon there. I'm going to put a 2-carbon branch there. And I'm going to do something sneaky and put my double bond right there. Now remember, when we highlight, we have to make sure that we are choosing the longest possible chain that includes the double or triple bond. So when I pick up my highlighter, you might be tempted to do this, but that would be incorrect. That chain does not include or highlight the double or triple bond. So we have to make sure that we have included that in my highlighting. So the longest chain that I can find is 1, 2, 3, and it doesn't matter which direction I go. I can go 4, 5, or I can go 4, 5. Now this way is going to work easier for me than the previous. Had I chosen to go the other way and gone this way, what I end up with is a branched branch. This is 1 branch point, and this branch has 2 directions. Now there are rules for that, but I don't want to get into showing those to you right now, although they do talk about them in your textbook. So I recommend you always pick the easiest path that you can to avoid that. There's always another option. And we're going to highlight in this direction. And I see there are 2 branches sticking off of this parent chain. So let's break this all down. I can see that I've got 1, 2, 3, 4, 5 carbons in my parent chain. And the word that means 5 carbons is pent. There is a double bond right here. And the word that means a double bond is present is ene. I need to say where that double bond lives. Now, in order to give that double bond the lowest possible numbering, I'm going to have to number in this direction. This is carbon 1, carbon 2, carbon 3, 4, and 5. My double bond is between carbons 2 and 3, so picking the lower number, this is 2 pentene. This part of the name right here is your parent chain.
Mr. Clark, to the front foyer, please.
So on your parent chain, we have two branches. We can see that we have this 2-carbon long branch called ethyl, and we have a 1-carbon branch called methyl. Who gets named first? Well, you have a choice. Alphabetical order says you name the ethyl first. Complexity order says you name the smallest first, so the methyl. It doesn't matter. In this case, both are considered acceptable. I'm going to choose alphabetical order. So my ethyl, moving up to the front, must go to the front of the name. I can see that it's attached to carbon 3, so this is 3-ethyl. My methyl is on carbon 4. So on carbon 4, I'll have a methyl. Be very careful, there's a letter and a number here to remember the dash. Those dashes are quite often what's forgotten about when kids are doing the structures. So this is the name of this molecule. Let's try another example where I give you a name and ask you to draw it. Okay. In this example, I'm asking you to draw an alkyne. I see the ending YNE that tells me somewhere there needs to be a triple bond between the carbons. I also can see from the prefix pent that the chain will be 5 carbons long, and this number tells me that that double bond will start on carbon 2. So let's start by drawing a 5-carbon parent chain. We always work our way from the end forward. So I'm going to draw a 5-carbon parent chain, 1, 2, 3, 4, 5. And now I have to decide to put the double bond, and it will start on carbon 2. That means it'll be between carbons 2 and 3. Now it doesn't matter if I choose to number from the left or the right, just so long as I've established a direction, I stick with it. In this example, I'm going to number from left to right. So my triple bond will go here. This is 2-pentyne. YNE, meaning we have a triple bond. But we're not done yet. I can see that we have di, which is 2 meth 1-carbon branches. YL tells they're a branch. They're both on carbons 4. So carbon 1, 2, 3, 4 has 1 methyl going one way and 1 methyl going the other way. These are 2 separate branches. They're pointing in opposite directions. They're both 1 carbon long. So this is now the structure for 4-dimethyl 2-pentyne. For practice, let's insert the hydrogens. This first carbon has 1 bond to another carbon and needs 3 hydrogens. It is considered acceptable to write the hydrogens in front of the carbon if your space requires. You could have also written the 3 hydrogens on the trailing end of the carbon. It would have still been considered correct. This next carbon has 4 bonds already, as does number 3. The middle carbon also has 4 bonds already. Remember, we always have to have 4 bonds only on each carbon. My end carbon here has only 1 bond to another carbon and requires 3 more hydrogens. It is the same with both these branch carbons. They have only 1 bond to other carbons and require 3 more hydrogens. So this is the complete structural formula for 4,4-dimethyl pentyne. We'll do one more example. Okay, I'm trying to be a little tricky here. When we look at this example, I can see lots of possible things that you might consider as a parent chain. But there are 2 rules we have to remember. One, we have to remember that triple bonds or double bonds, if they exist, must be included in the parent chain. 2, we have to remember that if there is a ring, it also must be part of the parent chain, even if that means we're bypassing a longer possible chain. Based on that criteria, the parent chain has to be this structure. That leaves the remaining part sticking off as a branch. Now that we've highlighted our parent chain, we can count the carbons. I can see that I have 1, 2, 3, 4, 5, 6 carbons. I chose to start numbering at this location because it gives my triple bond the lowest location in the ring. putting it between carbons 1 and 2. Because there are 6 carbons, I am going to use the prefix hex. Because there is a triple bond, it will have the ending -ine. The triple bond is between carbons 1 and 2, but this hexine isn't straight, it's a ring. So I'm going to use cyclo, and I'm going to say where that ine lives is at 1. This is 1 cyclohexyne, but I haven't yet named my branch. How do I name it? Well, this branch has 4 carbons in it. It is but for 4, and YL, meaning a branch. I can also see that it is attached to number 4. So in front of the name, I will say 4-butyl, being careful that I have a number and a letter side by side, so remembering my dash. This is for butyl 1-cyclohexyne. Alkenes can also do some very interesting types of configurations. We can have isomers in terms of moving the double bond around and still have the same amount of carbons and hydrogens. But these guys can also form special isomers called cis-trans isomers. Cis and trans isomers refer to what the parent chain is doing to the left and to the right of the double bond. In this case, when I highlight the parent chain itself, I'll grab my highlighter. My parent chain is up on both sides of the double bond. I can imagine a flat plane going through the double bond, and because my parent chain is on the up, on the left, and on the right, because it is on the same side on both sides, we use the prefix cis. This is cis-2-butene. In a case where I imagine that double bond going through, or my plane going through the double bond, and then highlight the parent chain. In this case, I'm up, across, and down. My parent chain appears to go across or to transverse the double bond. Whenever we go across the double bond, we use the prefix trans. This is trans-2-butene. It's hard to see the structures for cis and trans when we draw them. In these two molecules, we have changed some of the hydrogens temporarily to green so that you can see the difference between cis and trans and why they're actually different molecules. This first diagram shows 4 carbons. If you start by drawing a double bond, you can see that my 2 green ends, which probably would normally be considered a chlorine, but for this moment, let's consider them a carbon. One would be up in this direction, and one would be up in this direction. Now, in molecular model sets, green normally means chlorine, but we haven't taught you how to deal with any of the derivatives yet, so for the time being, we'll consider those to be carbon atoms. You notice how my carbons are both facing in the same direction from the double bond? I could take that same molecule and flip it upside down, and I would have it look like this. In both cases, this is the cis configuration. Cis because my parent chain is on the same side of the double bond. But there's no way to flip that molecule and make it look like the bottom version. In the bottom version, what we see is we've got my double bond, and my now green carbons go up on one side and down on the other. There's no way to flip the cis configuration and make it into a trans one. You can see from the picture that to do this, I would have to dismantle the model and rebuild it. I could also have flipped this trans one upside down and have it looking like this. Still, my carbons are on opposite sides of the double bond. Either way, this is the trans version because the carbons go across the double bond. Now, not every alkene will have a cis or a trans isomer. In this case, when I go and try to grab my highlighter and highlight through my parent chain, I know I have to highlight the double bond, and then I'm going to follow the longest possible chain. Although my parent chain is clearly pointing down on the right-hand side, there is no up on the left. So I do not get to use the prefix cis or trans. This is simply 2-methyl-1-butene. Also, where there is equal possibility of having a cis-trans isomer, I would also not use a cis-trans isomer prefix. So for example, if I have my double bond, and I'm going to go up on this side, up on this side, and I'm going to put what looks like a branch right here. I can tell my longest chain has 4 carbons. It is bute. There is a double bond. It is ene. The double bond is between carbons 2 and 3. It is 2-butene. And there is a methyl group also on carbon 2, 2-methyl. Squeeze that in there. But is it cis or trans? Well, that depends on what you consider to be the parent chain. If I consider this the parent chain and this as a branch, well, then it was a trans isomer. But it is just as likely that I consider this to be the parent chain and this is a branch. Because both possibilities are equally as likely, we do not use the prefix cis or trans. So cis and trans is only used when there is a clear distinction. Now there's lots of practice on naming and drawing alkenes and alkynes, as well as practice with cis and trans isomers in your workbook on pages 15 to 26. Alkanes and alkenes and alkynes are our aliphatic or straight chain hydrocarbons. In our next lesson, we'll be learning about the aromatic hydrocarbons, the ones with the fancy ring structure.